Okay, so I welcome all of you again to this section. Okay, the final chapter for thermodynamic MEC451. Okay, and we have already started with this particular chapter. Okay, let us recapitulate what we mentioned last time when we met. We started by making a difference between gas power cycle and steam power cycle. So in gas power cycle, the working fluid basically gas. Okay, and then we mentioned that all actual gas power cycles do not follow real thermodynamic cycle. So we need to impose certain assumptions, okay, the air standard assumption on these systems so that we will be able to analyze the thermodynamic properties of the system. Okay, so one of these assumptions is that air continue to work or behave as an ideal gas in the system. In other words, the working fluid is basically air. Okay, throughout the cycle, compression, expansion processes, heat addition process is replaced. So the combustion process is replaced by a heat addition process. Okay, then we look at the various cycles involved in the transformation of this actual cycle into ideal cycle. So the ideal cycle of the gas power cycle is called the Brayton cycle. And all the cycles associated with the Brayton cycle are reversible. All right. So then we look at regeneration or regenerative gas power cycle. Okay. And also we look at reheating, regenerative, okay, gas power cycle. So we'll have an opportunity where we will solve some questions related to these power cycles. If not today, then next week. Okay, and then we started with the analysis of steam power cycle. Okay, first we look at the concept of the Carnot cycle. So I've told that the Carnot cycle is the theoretical cycle for steam power cycle, and it has the highest efficiency, okay, compared with any other actual steam power cycle. Because of what? Because all the processes involved in the Carnot cycle are reversible. But there are so many weaknesses, okay, inadequacies of the steam power cycle, of the Carnot cycle. Okay, one of the weaknesses of the Carnot cycle is that it cannot be operated, okay, at a very, very low temperature. Okay, so state 1 and state 2 is a constant temperature heat addition process, and the fluid between state 2 to state 3, so the fluid that enters the gas turbine or the turbine is at a saturated liquid state, saturated vapor state. So when it expands, a large amount of it is mainly water. So this cannot be used, or it cannot be, you cannot get any high efficiency from this cycle. And then also the fluid that enters the pump, okay, is in the saturated liquid vapor mixture. So this is not permissible in any engineering field where you filled a pump with saturated liquid vapor mixture. Okay, so the pump will be cavitated, and so on. So we have to make a modification. So modification of the Carnot cycle is what we call the ideal Rankine cycle. So what are the basic modifications here? Here the fluid is cooled down continuously in the condenser until it reaches state 1, saturated liquid state, before it goes into the pump. and then heat is added at constant temperature, constant pressure, but at varying what? Temperature. And again, the fluid is expanded from superheated to saturated liquid vapor mixture. Okay? So today we want to look at the energy balance for this control volume or for the steam power cycle. Okay, we have already visited these systems in chapter 3. So this is just a recapture or recapitulation of what we did in chapter 3. So now we want to look at the energy balance for a pump. Okay, so what is a pump? A pump is a device which is used to pump a fluid at in order to increase or elevate the pressure at the exit. All right? So the energy that enters the pump is given by E1, let's say, and the energy of the fluid that leaves the pump is given by E2, E.2. Okay? And similarly, the work input to the pump is W in dot, I'll say. So the energy balance for this system is given by total energy in, okay, it should be equal to total energy at the exit, at the outlet. Okay, so what are the total energy in? What are the total energy at the inlet? We have E1 is coming in, okay, E1 plus W in equals to what? E2. So what is this E1 and E2? E1 is simply mass flow rate of the fluid at the inlet times the enthalpy H1 plus the kinetic energy plus potential energy term. All right. Similarly, E2 gives us mass flow rate M2 H2 plus kinetic energy at the exit plus potential energy. But the change in these potential and kinetic energies are equal to 0. So eventually, E1 is nothing equals to mass flow rate times M1 times H1. And similarly, E2 equals to M2 times H2. All right. So if you substitute into this equation above, so eventually we will have E1, which is M1 H1 plus W in equals to M2 H2. So eventually W in equals to what? M2 H2 minus M1 H1. But then for steady state condition, M1 equals to M2 equals to M. So we can have our W in is nothing equals to M into bracket H2 minus H1. All right. So we have done this already in chapter 3. So it's just a recapture. Now, we have also noted that the work input to the pump can also be expressed in this form. You understand me? It can also be expressed in this form. We have also shown that already, so I'll not go into such detail. Okay, so we have over here, we have to take note of this, that the work input to a pump is the same as the mass flow rate times specific volume at state 1 times the change in the pressure. All right, so it means there is a low pressure and this is the high pressure. Now, next, we look at the energy balance for the boiler. Also, this is not a new thing we have done already. The energy balance for the boiler is like this. So in the first case, what is the boiler? So the boiler is the device which is used to produce superheated steam, okay, that is used to operate the turbine. All right. So similarly, the energy balance for the boiler can be expressed like this. All right. So if you take this to be the boiler, all right. So we have the fluid which is coming from the pump at state 2 and exits the boiler at state 3. All right. So now in this boiler there is heat input, Q in. All right. So if you look at the energy balance, here again I have E2, here I have E3. So eventually the total energy in equals to E2 plus Q in equals to what? E3. So eventually Q in is given by mass flow rate M3H3 minus M2H2. Again, at steady state condition, we have MH3 minus H2. All right. So now this Q in is the same as can be expressed in terms of the boiler efficiency times the mass flow rate of the fuel and the calorific heating value. Okay, so that's what we have over here. So this Q in is the same as the Q from the furnace or the boiler, right? So M is the mass flow rate and CHV is the calorific heating value. Similarly, we can look at the expansion in the turbine, all right? So if you take the turbine to be this, so the fluid enters the turbine at high pressure and temperature, and then it leaves. Now, this is W out. All right? So you have E3 over here and here E4. So this E4 is mass flow rate, M4H4. This gives us M3H3. All right? So the energy balance again gives us, we have M3H3 equals to W out plus what? M4H4. So now W out gives us M into bracket, I'll say H3 minus H4. Okay, so that is very easy to determine the energy in the turbine. The work output from the turbine. So the final one is the condenser. Okay, so now the condenser is a device which is used for cooling. So the steam enters the condenser, all right. So then it is cooled down into saturated liquid. Okay. So now we have cold water is fed into these tubes, and then the hot water flows across the tube, and then it is condensed, and eventually it comes out like this. Okay, so if you want to establish the energy balance for the condenser, you can simply make a schematic diagram of the condenser like this. Schematic diagram of the condenser, let's say like this. Okay, the fluid from the turbine is coming at state 4 and it is leaving at state 1 into the pump. So here we have Q out, Q out. All right. So this Q out can be determined is the same as Q for the condenser. Okay. And we can determine also the energy balance for this. Here we have E4, E4, and this is E1. So how to determine the energy balance? We will have E4 plus, E4 equals to Q out plus what? E1. So eventually, E4 is nothing, Q out gives us mass flow rate H4 minus H1. Okay, so that is this. Now, another way in which we can describe the condenser is like this. You see, the condenser is a heat exchanger. Okay, let me sketch and see. Behaves as like a heat exchanger. The hot water comes from the turbine and enters. So let's assume this is the hot water tube. All right. And then it goes to the pump. Okay. So what we need to do is like this. We need to also know that there will be some cold water that comes into the condenser. So cold water will be input into the condenser and it will be flooded all over the shell part, then it will exit like this. So the amount of energy, the energy lost by the hot water is equal to energy gained by the cold water. All right? So the energy which is lost by the hot water is normally given by this Q out. So the energy gained by the cold water is given by the Q condenser. And they are the same. If 5 kilojoules of energy is lost by the steam, 5 kilojoules of energy is gained by the cold water. And this can be expressed as mass flow rate of the cold water, specific heat capacity of the cold water, times delta T. So this delta T is T in here and T out on this side. Okay, so to find the efficiency, okay, so we know that efficiency of the system equals to W net. What is this W net? The W net is the difference, okay, between we have W out, okay, minus the work input, okay, to the pump. So the net work is the work from the turbine minus the work input to the pump. And this equals to W net. Okay, this is the W net. That's how it is defined. So now, eventually, we will have the efficiency equals to W net divided by Q in. Okay, so Q in is the difference between the enthalpy. Okay, so we have already determined that. Okay, that is the boiler states. Now, we will come to these questions again later on. Okay, so we have the actual vapor power cycle, okay, differs from the ideal cycle as a result of irreversibilities. Yes, so in this situation, just like we did for the gas power cycle, in the steam power cycle, we also have irreversibilities. When we say irreversibilities, what do we mean? It means there is pressure drop, there are losses because of pressure, there are losses due to friction, and so on and so forth. Okay, so there are so many agents of irreversibility of a system. But we will focus our attention on the irreversibilities associated with the turbine and the pump. All right? So now, if you consider the pump, the isentropic efficiency for the pump equals to the actual work, the reversible work, which is Ws, this is the Ws, divided by WA. And WA is what? That is the actual work input to the pump. All right. Similarly, if you consider the expansion in the turbine, there will be isentropic expansion, which is this, and there will be actual expansion, which is this. So this is WA divided by WS. And it's nothing, it's the change in the enthalpies at various states. All right? Yes, again, we will be coming to this questions. Now, there are various opportunities that are available for the determination of or increasing the efficiency of the steam power cycle. Okay, one of such opportunities is that if we continue to reduce or lowering the condenser pressure, increases the efficiency. So if you increase the average temperature at which heat is transferred to the working fluid in the boiler, or decreasing the average temperature at which heat is rejected in the working fluid in the condenser. So these are two primary information, very important. You see, for the initial state, assuming this is P1, initial pressure, and this is P2. Okay, so this is constant pressure line. P2 we know equals to P3, and here P1 equals to P4. All right. So if we stop over here, then the efficiency which we'll get will be lower than if we continue into this state. You understand? Because then the network will increase in proportionate to this shaded region. Okay, so that the more we expand the fluid, then the more the efficiency we are going to have. Okay, so we eventually conclude that lowering the condenser pressure increases the moisture content of the steam at the final stages of the turbine. So if you continue to lower the temperature, lower the condenser pressure, then there will be, we will have a situation where there will be more vapor present in the turbine, okay, which is again not desirable for the turbine. So there is a limitation on this as well. Now we have superheating the steam to high temperatures. Also, if our initial heating process is this, okay, you heat the fluid from state 2 all the way to state 3, and then you expand it. Then, due to this expansion, you get a certain efficiency. Let's say efficiency number 1. But if you go on, continue to increase more superheated, then you see that there will be more work output. So let's say if this is efficiency number 2, it means efficiency number 2 will be greater than efficiency number 1 because of this more expansion that we have in the turbine. So superheating the steam to high temperature also increases the efficiency, okay, of the cycle. And then we have increasing the boiler pressure. How do we increase the boiler pressure? So this is our initial pressure line. Okay, this is the constant pressure line for the boiler. So if we increase this pressure, so it means we will be operating along this direction. All right. So high pressure, there will be a decrease in W net because this line is shifting to the left. You understand? And so you see that halfway after the expansion of the fluid, then you will have a lot of vapor present. So it means increasing the boiler pressure. So to some extent it helps, but to a large extent it's not desirable because there will be steam, moisture. Okay, for a fixed turbine inlet temperature, the cycle shifts to the left and the moisture content of the steam at the turbine exit increases. This effect can be corrected by reheating. Yes. So this is the situation. Let's say if we expand the fluid at this state, it continues to go down. We can reheat it up to state 3 before again expanding. Okay. Now we look at so when we say reheating, so this is what we mean by reheating. First, we expand the fluid in the first turbine and then reheat it to a high temperature at constant pressure before again it is expanded again. All right. So this is what we call a reheat, ideal reheat Rankine cycle. Ideal reheat Rankine cycle. Okay, ideal reheat Rankine cycle. It's given by this diagram. So here, how does the situation work? We have a pump over here which feeds the boiler with water, So then the water is heated to superheated. It enters the first high pressure turbine, and then the fluid is expanded. So here, watch out on the TS diagram. See, we have the compression isentropically from state 1 to state 2. Okay? And then we have constant pressure heat addition from 2 to 3. From 2 to 3, we have constant pressure heat addition. Then eventually we will have expansion in the what? In the high pressure turbine from 3 to 4. After which the fluid is sent again to the boiler for reheating. So this reheating is carried out such a way that the temperature of the fluid is again elevated. Again, but this is done at constant pressure. So it means P4 and P5 equals to P5. Take note of that. Before the fluid enters the low pressure turbine, and then it is expanded again. Before again it is cooled down in the condenser. So this is the normal practice. If you go to the industry, if you happen to work with a company that is based on steam power cycle, then you will see all these things there. Now, Q in can be calculated from Q primary. Q primary means that the Q from the boiler. This is the Q primary. Okay. And then plus Q reheating. So there will be a reheating again over here. And this equals to H3 minus H2, which is the difference in the enthalpy between these two states, plus H4, H5 minus H4. Okay? Then the total work output is the combined effect of both turbine number 1 and turbine number 2. Okay? So now we come to, again, ideal reheat Rankine cycle. Okay, so we can have multi-stage expansion. So just like we have multi-stage expansion in the gas power cycle, here also we can have multi-stage. But again, here it means you can have 2, 3, 4, 5, up to a certain number of turbines. Okay. So now, eventually, we should know that there is a limitation. So for everything, there is a limitation, especially limitation imposed on the metallurgical properties of the turbine. Extremely high temperature is not desirable for the running of the turbine. Okay? So we say the single reheat in a modern power plant improves the cycle efficiency by 4 to 5% only. Okay? That is by increasing the average temperature at which heat is transferred to the steam. And the average temperature during the reheat process can be increased by increasing the number of expansion and reheat stages. Okay. So the use of more than 2 reheat stages is not practical. So the theoretical improvement in efficiency from the second reheat is about half of that, which result from a single reheat. Okay, so take note of that. So that the optimum reheat pressure is about 1/4 of the maximum cycle. Okay, so this is again an example we'll look into. Now let's look at ideal regenerative Rankine cycle. ideal regenerative Rankine cycle. So in this situation, we have, let's say, the steam power plant is extracted from the turbine. Okay, so for regenerative Rankine cycle, okay, we say that the steam power plant, in the steam power plant, steam is extracted from the turbine at various points. So it means that when the turbine is undergoing expansion, we can remove some of the fluid at very, very extremely high temperature and use it for reheating, okay, or for other heating purposes. So the steam which could have been produced, which could have produced more work by expansion further in the turbine, is used to reheat the feed water instead. The device where the feed water is reheated by regeneration is called feed water heater. Okay? And we have open feed water heater and closed feed water heater. So we will not go into such details, okay, in solving questions, but we will only introduce ourselves to it. So this is open feed water heaters. Okay, so your final exams will not, there won't be any question related to this. Okay, this particular site. Okay, so we can have two turbine, one pump, and so on like that. And one turbine, one pump, but feed water heater, mostly, I think there wouldn't be any question on that. So, but again, it is worth not knowing. Okay, so we need to know something on that. So here we have open feed water heater. So what means is that here first, the fluid in this so the fluid at state 1 in the pump is pumped to state 2, and then it is reheated. This is preheating. You see, we take some amount of superheated steam from state 6 and add it to this cold water. So then the temperature of this fluid is elevated and it goes to state 3. Here is it. Now, the fluid again is pumped through the pump number 2 into the boiler. So then again, heating continues up to state 5. Before again the fluid is expanded, okay? So during the expansion, part of the fluid is taken to state 3, and the rest continues to expand to state 7. Okay. So eventually we have Q in equals to H, difference in enthalpy. Q in equals to the difference in this enthalpy, that is H5 minus H4. And the Q out. So yes, so this is yes, so our Q out is going to be a function of this. If Y is the fraction of the fluid which is extracted over here, then we will have 1 minus Y of the amount of fluid that will be flowing over here is this. Okay, because the total mole of the fluid has to be 1 over here. So out of this 1, we extract a certain percentage, let's say Y. And if this y equals to 10%, then there will be 100 minus 10%. That will be 90% will be flowing in the condenser. So it means that we'll have 1 minus y times the difference in enthalpy over here, H7 minus H1. So now the total work output by the turbine has to be expressed in terms of these parameters. H5 minus H6, okay, H5 minus H6 plus H6 minus H7 times this fraction, which is extracted. And the work added to the pump is the, for pump number 1, we have 1 minus y times this, the work input plus the work input to the pump. And note that y equals to mass flow rate at state 6 divided by mass flow rate at state 5. Okay. So that the individual pump, the work input is given by this. Okay. So this is an example. And for the closed feed water heater, we have another type of closed. So this is a closed feed water heater. Closed feed water heater means that the fluid which we extract over here has no direct contact with this fluid. Instead, we put a heat exchanger. So heat will be transferred from this hot fluid to this cold fluid. Okay. So that over here we will have the pump number 1 pumps the fluid from state 1 to state 2 through isentropic process. Then from state 2, there will be heat transfer, okay, to the fluid as it passes this heat exchanger. That's the closed feed water heater. So means its temperature will be elevated gradually up to state 9. Its temperature is increased. And the temperature of this fluid will be decreasing. All right? So it will be increasing up to state 9. And then it continues when it reaches state 7. Then this fluid goes to the pump. And then again, it is mixed at state 5. More temperature increasing. Before eventually, we add more heat to it in the boiler and elevate the temperature to state 6. And then eventually again, we have expansion in the turbine up to state 7, and part of it is extracted to state 3. Okay? And the expansion continues all the way to state 8 in this way. Okay? So this is also an example of closed feed water heater. Okay, so multiple closed feed water heater and open feed water heater. So it's a combination. Okay, so this is a bit more complex than those we have been looking at previously. Okay, so I think this brings us to the end of this particular slide. Okay, so let me see if we can solve one or two questions before we leave. And let me upload a particular question. So 1 minute. And let me see this question we can discuss. So 1 minute. So December 2018. I have a question over here. Pass your question. So I'm coming. 1 minute. So can you see the? Oh, sorry. I have to upload it again. Sorry. So let me upload it. Yes, so let us see this question. So the first part, this is December 2018. Final year exams, December 2018. Okay, December 2018. All right, so final year exam. Then again, the first question says, with the aid of diagram, briefly explain the working principle of a gas turbine engine. So this you can easily look into your table, or sorry, your lecture notes. So the main components involved in the gas turbine is the compressor, okay, and then we have the combustion chamber, and we have the turbine. You understand me? Okay, so very simple one, you can describe like that. Okay, so now we are told in the next question, table question 2B is tabulated in such a way that the specific enthalpy of a typical gas turbine engine, okay, is given. So we have the gas turbine engine Breton with intercooling and reheating. So we have Breton cycle with intercooling and reheating. So overall pressure ratio is given by this, and atmospheric temperature is this, and pressure is also given. Now the mass flow rate of the fluid is given, and we have the properties for the compressor. There are two compressors, identical, and their isentropic efficiency is given. Similarly, we have three identical turbines. You understand? So whose efficiency is 90%. And then we have the natural gas, okay, the calorific heating value, mass flow rate. So this particular data will be used to calculate Q in, which equals to mass flow rate of the fuel times what? The calorific heating value. Okay, so times the combustion efficiency, again times the calorific heating value. Right? So now let us see the overview of this question. Now as long as that we know that we have, you see, anytime they mention efficiency of the turbine or compressor means they are referring to isentropic efficiency for the turbine and isentropic efficiency for the compressor. So it means you have to consider both cases. All right? So both isentropic efficiency for the turbine and the compressor respectively. And here we have how many compressors? 2 compressors. And how many turbines? 3 turbines. So now, to draw the diagram on a TS diagram, it's going to look like this. So first, we have compression in the first compressor 1 to 2, and there is intercooler. And then the fluid is again compressed from state 3 to state 4. Now, we are not told that we have any reheater, regenerative. There is no regenerative. Regenerative is absent. No regenerative. So if there is no regenerative, then the question becomes very easy. Otherwise, if there is regenerative, then we need to consider it. Okay, listen to the question carefully. It says, table question 2B is, okay, tabulate the specification of a typical gas turbine engine with the aid of TS diagram for this cycle, determine the total compressor work, the rate of heat supply to the cycle from the combustion chamber. Okay, the maximum temperature of the cycle, the total turbine work output, and then the network output, and the thermal efficiency. So cleverly, we need to draw this. So we have, this is the heat input side from 4 up to state 5. And there will be expansion in the first turbine. So we'll have state 6. Okay. So now, again, there will be reheating up to state what? State 7. Before there will be another expansion up to stage 8, and then another reheating before the final expansion. So this is 9 and 10. So we have only 2 compressors and 3 turbines. So eventually, the heat is rejected to the surrounding from state 10 to back to state 1, like this. Okay, so we have to consider the fact that there is isentropic expansion. Means we have this is 6S, and this is 6A. And this will give us 8S and 8A. And similarly, we will have 10. So let me sketch it. So maybe after this sketch, we will stop and then we will continue next week with this question. Okay, let me just give you a background of the question. Then maybe you can try at home. So this gives us, this is number 5, this is 5S, and we have 5A. And this is, okay, 8S, and then we have 8A. And similarly, we have 10S, and this gives us 10A. All right. So similarly, the same thing for the compressors. This is 4S and 4A. And then we have over here also isentropic expansion, and this is the actual expansion, 2S, 2A. So this is the temperature entropy diagram for the cycle. Okay. So now we need to determine the compressor. Yes, one thing you need to know, we are told the overall pressure ratio equals to 16 Okay, this is very, very, very important. This is very, very, very important. What is definition for pressure ratio? For a single turbine or compressor, if you take a single compressor like this, okay, where the inlet pressure equals to P1, exit pressure equals to P2. So it means pressure ratio will be equal to P2 divided by P1. All right. So now, what we need to know is that here we have two compressors. So it starts from state 1 to 2 for compressor number 1, and then 3 to 4 for compressor number 2. So that for this particular case, when we are told that overall pressure ratio, overall pressure ratio pressure ratio, okay, equals to 16, it implies that P4 divided by P1 equals to 16. You understand? So P4 divided by P1 equals to 16. But this P4 divided by P1 can be expressed in terms of P4 divided by P3, okay, times P3, let me see over here, yes, times P2 divided by P1, okay? We can express in this way, okay? So let me explain. You see, whenever we have a TS diagram, I think you know, on a TS diagram, for a constant pressure line is this. Okay? So if I have a point over here, say point number 1, and then I have another point over here, number 2. So since this is a constant pressure line, it means P1 equals to P2. The same thing over here. The pressure at this state, the pressure, this line corresponds to a constant pressure line. It means P3 and P2, they are the same. P3 equals to P2S equals to P2A. Okay, P3 equals to P2, okay, equals to P2S equals to P2A. Okay, so if P2 and P3 are the same, so it means I can cancel this, and then I'll go back to P4 minus P1 like this. Okay, so I don't want to do the cancellation. So I'll write P4 divided, this is very important for you to take note. P4 divided by P3 times P2 divided by P1. You understand me? P2 divided by P1. So now, this will help us to identify the individual pressure ratios. Okay. So, this gives me P4 divided by P3 times P2 divided by P1. So, but consider the first compressor, RP1, RP compressor number 1. Compressor number 1 equals to P what? P2 divided by P3. Sorry, P2 divided by P1. And then RP for compressor number 2 equals to P4 divided by P3. Okay? So it means that this is the same as, let me see, we have P4 divided by P1. But we are told that, let's see over here, let's see. So somebody is just coming, long time, almost finished. Okay, so we have P4 divided by P3 times P2 divided by P1. Okay, now this equals to 16. Yes, overall pressure ratio equals to 16. Okay. So now, but one thing you need to know is that the pressure ratio, RP for compressor number 1, is the same as RP. So it's the same as, sorry. So it's the same as RP for compressor number 2. So this discussion is very important. RP compressor number 2. So if they are the same, so it means that they can have 16. It means RP for compressor number 1 times RP compressor number 2 equals to 16. All right? So then eventually I'll have RP for the compressor, okay, square, I'll say, because they are the same, raised to the power 2 equals to 16. So RP for the compressor, I'll say compressor, equals to square root of what? Square root of 16. And that gives us square root of 16 equals to 4. So it means that pressure ratio for compressor number 1 equals to P2 divided by P1 equals to 4. Similarly, pressure ratio for compressor number 2 equals to P4 divided by P3 also equals to 4. This is very, very important. Okay. So now, if we have to determine the work, the total work of the compressor. So this is the compressor. So compressor, if they say we should find the total work input to the compressor, then it means they want us to find this WA. Okay, so the WA for the compressor number 1, and also WA for compressor number 2. Okay, so that's the total work input to the compressor. So do you have W total, okay, to compressor equals to W, okay, WA compressor number 1 plus WA compressor number 2. Okay, so what is WA compressor number 1? It is given by mass flow rate of the working fluid times the change in enthalpy. Enthalpy means H2A minus H1. Okay. So now, this can be calculated as, since this is an ideal gas, so we can write it equals to, mass flow rate, specific heat capacity of the air, T2A minus what? T1. All right? Similarly, so now we need to determine T2A, because T1, I think T1 is giving. Yes, T1 equals to 27 degrees Celsius. So that is 300 Kelvin. Okay, T1 is known. Cp for air equals to 1.005 kilojoules per kilogram per Kelvin. And T1 equals to 300 Kelvin. Okay, mass flow rate of the fluid is given. Mass flow rate, yes, 185 grams. Mass flow rate, 185 grams per second. Okay, we have to express in kilogram. So 185 grams per second equals to 0.185 kilogram per second. So now we need to find T2A. So how do we determine T2A? By relying on isentropic efficiency. You understand? So this is very, very important, to rely on the concept of isentropic efficiency. Okay, so isentropic efficiency for compressor number 1, I'll write over here, isentropic efficiency for compressor number 1 equals to WS, I'm very sorry. It's always the smaller value divided by the bigger one. Okay, so this gives me so we have WS divided by WA. Okay, so that is it. And so this gives us for compressor number 1, and then for compressor number 2, the efficiency for compressor number 2 also gives us WS also divided by WA, but with respect to state 4 and state 3. So now eventually we'll have, for compressor number 1, isentropic efficiency, compressor number 1 equals to WS divided by WA. This gives us mass flow rate, H2S minus H1 divided by mass flow rate, H2A minus H1. So mass flow rate is the same. You convert into Cp, T2S minus T1 divided by Cp T2A minus T1. All right? So this is equal to, they will cancel. Now the whole of this equals to, we know the temperature, the efficiency for the compressor is 85%. So we equate this to 0.85. So bear in mind, we are looking for T2A. So T2S is not known. So since process 1 to 2 is isentropic compression, so we use the isentropic equation. We have 1 over P2 over P1, okay, P2 over P1 equals to V2 divided by V1 raised to the power K equals to T, V1 divided by V2 divided by V2. And this gives me T2 divided by T1, all raised to the power K divided by K minus 1. So here we know the pressure ratio. So we should use instead this one, this equation. So we can say, so I'll say this is T2S. Okay? So I'll take this out. I'll have P2 divided by P1 equals to T2S divided by T1 raised to the power K minus 1. So what I'll do, I'll multiply this by K minus 1 divided by K. Do the same, K, multiply this by K minus 1 divided by K. So all this will cancel out. So eventually, T2S equals to the pressure ratio, P2 divided by P1, all raised to the power K minus 1 divided by K times T1. Okay, so this is the situation. So now, pressure ratio, this equals to 4 into bracket 1.4 minus 1 divided by 1.4 times 300 Kelvin. Can somebody calculate this for us? Anybody with a calculator? Scientific calculator. What is the value?
445.
How much? How much?
445.
445.
5.8.
0.8. Thank you. Kelvin. All right. So now we will substitute this T2S into this equation. So we have 0.85 equals to T2S. Okay, we know T2S already, sorry. 445.8. Sorry, so we have 0.85 445.8 minus 300 Kelvin divided by T2A minus 300 Kelvin. So can somebody calculate T2A for us? Yes. T2A.
471.53.
471.53.
3. Yes.
Okay, thank you. So now we have calculated T2A. So with this, we can determine our WA. Okay, so my WAC for compressor number 1 equals to mass flow rate, okay, MCP T2A minus T1. So this gives me, there is noise in the background. Can you mute your mic, please? So we have 0.185 kilogram per second, thank you, times specific heat capacity for air, 0.005 kilojoules per kilogram per Kelvin, times T2A 471.53 minus 300 Kelvin. So what is the result? Please tell.
$31.89.
How much?
$31.89.
31.89.
Yes.
Okay, thank you very much. So that gives us in kilowatt. All right. So now, you see, since both compressors have the same pressure ratio, so it means they will have the same WA. Okay, since RP1 for compressor number 1 equals to RP compressor number 2. So it implies that they will both have the same WA. So it means WA for compressor number 1 will be equal to WA for compressor number 2. So that the total work input, which we want to calculate, the total compressor work input. Where is it? Yes, so total compressor work input. Okay, so this gives us the total compressor work input. Okay, so W for compressor. Okay, I'll say W compressor total equals to WA compressor number 1 plus WA compressor number 2. So this gives us 2 times 31.89. How much is that? So that gives us about 60?
63.78.
How much?
63.78.
63.78. Thank you very much. So kilowatt. All right. So that is it. Very easy. One thing about this type of question, they are very easy, but they take a lot of time. Okay. If you understand it, very, very easy. And then the next question is to find the rate of heat supply to the cycle from the combustion chamber. All right. So rate of heat supply. And then first, maybe we should determine the work, Okay, so we can determine also the rate of heat supply to the combustion chamber. Let's see over here. I have told you, so one of the options which is available, okay, the heat supply to the combustion chamber, it is actually the amount of heat which is supplied to the amount of heat added to the system. It does not start from here. The actual heat starts from 4A. 4A until it goes to number 5. Okay? And then also, we have to know that there is reheating over here. Okay? Reheating from state, what I did was wrong over here. So this is supposed to be 6. Very sorry. This is supposed to be 6. Okay, yes, so then 7. So from state 6 to 7, there will be Q in. Also from state 8 to 9, there will be another Q in. All right. So the total amount of heat added, total amount of heat Q in is actually equals to the Q primary plus Q from stage, let me see, 6 to 7 plus the Q due to, let me see, stage 8 to 9, 6 to 7, 8 and 8 to 9. Okay, Q 8 to 9. And the Q primary is Q 4, 5 plus Q 6, 7 plus Q 8, 9. Okay, so I think we will stop over here, and inshallah, we will continue with this particular solution in the next class. Okay, so if there is any question, please let me know. Okay, is there any question so far?
No, sir.
All right.
No, sir.
Okay.